So we have two equivalent equations for describing the entropy of an ideal gas, of a monatomic ideal gas, right? And we developed these equations by combining quantum mechanics and thermodynamics. All right, and so using these equations, we could derive, several sort of classical equations that you've seen before. Okay, so here I'm once again going to paste the Sackur-Tetrode equation, right? And what we're going to do now is we're going to apply apply some of the properties we know that hold for entropy. So for example, we know that the partial derivative of entropy, actually not molar, of entropy with respect to volume at constant internal energy and n, if we go out and perform this derivative, we get the following relationship: nkb over v. Right? That's just what we get when we perform the partial derivative. We also know that for entropy, this partial derivative, based on our fundamental equations for entropy, is just equal to pressure over temperature. If we rearrange this equation, we get the following relationship: PV is equal to N kBT, right? And then what I'm going to do here is then I'm going to multiply the right-hand side by the Avogadro's number divided by Avogadro's number. So I'll write the divided by Avogadro's number there, and then I'll put the Avogadro's number at the top here. And so this divided by this is just 1, right? So we're just multiplying the right-hand side by 1. We're not changing the value at all. But by doing this, we now have the following. So by definition, the Boltzmann constant multiplied by Avogadro's number is just the gas constant. And here, n, which is the number of molecules in our system, divided by Avogadro's number, that gives us moles. And so our equation now is PV is equal to nRT. And so using the Sackur-Tetrode equation and the properties of entropy, we now derived the ideal gas law. Okay? All right, so that's, one example of the utility of the Sackur-Tetrode equation. What we could also do is we could take the partial derivative of entropy with respect to internal energy at constant V and n. And so here, it's more useful to use this form of the entropy equation because it has a u built in here. And so when we take that partial derivative, we get 3/2 n kBT, or nkb over u. All right, so that's just mathematically what we get by taking the partial derivative of the Sackur-Tetrode equation. But we also know that one of the fundamental properties of entropy is that ds du gives you inverse temperature. And so if we rearrange the equation, what we get is that the internal energy is once again equal to 3/2 kB n T. Okay? All right, and so this is the same result that we got previously on the other page when we did the transformation directly from the total system partition function. Right? But what I want to do here is I'm going to do the same trick we did with the ideal gas law, where I'm going to multiply this equation by Avogadro's number over Avogadro's number. Okay? And so once again, when we have Kb multiplied by Avogadro's number, that's going to give us R. And n divided by Avogadro's number is going to give us the number of moles. So what we have here is number of moles times 3/2 R times temperature. Okay? All right, and so this equation looks funny, but actually the reason I wrote it in this format is because this 3/2 R, by definition, is actually the heat capacity for a monatomic gas. Right? And so that value is about equal to 12.47 joules per mole K. Right? Right, and so that that might just seem like a sort of random grouping of parameters saying it's the heat capacity. But if you go out and look up the constant volume heat capacity for a molecule or a chemical like helium, you'll find that its heat capacity is about 12.47, right? So it's kind of crazy, but using the ideal gas sort of framework, or the total partition, the Sackur-Tetrode entropy equation, we could actually just estimate our heat capacities fairly easily, right? And so essentially what we find here is that the internal energy is equal to NCVT. Right? And this is the sort of result that we got previously just using techniques of classical thermodynamics. But here, we're able to bridge the more molecular perspective, and we're still able to get these same results. The final partial derivative I want to look at is ds dn. So this is a constant u, constant v. So when we do this partial derivative, we get minus kb ln, and then we get all this stuff within the natural log. Three halves volume over n. Okay. All right, and so within this natural log, this is what we get just by performing the calculus. And when we do it, we get this collection of constants right here. Right? This collection of constants has because it's kind of seen a lot when dealing with statistical mechanics, this collection of constants actually has the name of the de Broglie wavelength. Okay? All right? And it's abbreviated by capital lambda. And it's a wavelength because it has units of length. Right? So, in terms of like nanometers or things like that. And you'll see that essentially the wavelength of the particle is going to be a function of its mass and its temperature, which we know to be true. Okay, in any case, so by doing the partial derivative, we get this sort of expression. And we know one of the basic properties is that ds dn gives us the chemical potential divided by temperature. And so as a result, we now have an expression for the chemical potential for an ideal gas. So it's going to be V, and technically the de Broglie wavelength is this to the 1/2. So let me highlight that in blue. Okay. And so we're going to have volume here, and on the bottom we'll have the de Broglie wavelength cubed so that the units match, and then we'll have n here. Okay? All right, and so this is an expression for the chemical potential, and I'll box this equation in. Okay. One thing I'll note, so we have two different length scales we're comparing here. The volume of our system divided by this de Broglie wavelength. Right? What I will say is that if the volume of your system divided by n, so here, if that's much smaller than lambda cubed, right, so this is much smaller than this, you'll get a very tiny number in the ln, right? And so this will go towards negative infinity, or since you're multiplying by a negative here, your chemical potential will then skyrocket towards infinity. And so essentially, you kind of reach a singularity in your chemical potential calculation, right? The model breaks down. And essentially, if that is the case, the models that we developed here aren't sufficient for describing the system. And instead, you need to account for more complicated quantum mechanic effects. All right, that's going to be outside the scope of this class here. All right, but I just thought I'd mention it as well. In any case, when we're dealing with an ideal gas, we have this volume over n term, and as we saw earlier, we could actually relate volume over n to these things here, using the ideal gas law. So can replace V over n with kBT over P. Okay? And so if we plug that into the chemical potential equation, natural log of P, right, and we're going to split up, since we're dealing with a logarithm, I'm going to split them up into different parts. So kBT natural log of P, kBT ln of, now we have another kBT on the inside, divided by the de Broglie wavelength cubed. Alright, so this is what the expression looks like now. You'll notice we're dealing with a bunch of ln's, and this, we have pressure there, and this is going to give us also units of pressure on the inside. But since we're dealing with natural logs, on the inside it needs to be unitless. And so to avoid that problem, what we're going to do is we're going to add the following. So kBT, essentially we're going to add the natural log of 1. And we know by definition that's equal to 0. Right? But for the natural log of 1, what we're going to add is the ratio of P naught over P naught. And then taking advantage of our log rules, I'm just writing it like this. And the P naught we're dealing with, this is known as a standard state pressure. It's essentially a sort of reference pressure for our system. Okay? And so what I'll do is I'll combine, this P naught here and this P naught here. Okay? All right, and so what we get is that the chemical potential is equal to kBT natural log of P divided by P naught minus kBT natural log of kBT divided by lambda cubed P naught. All right. For the second term, for a given temperature, all these things are just going to be, constant, right, for a certain temperature. Right? And so I'm going to define the second term as a standard state chemical potential. Right? So just like we had a reference pressure, we also have this reference chemical potential. Right? And essentially what this standard state chemical potential does is describes properties that are internal to the molecule. So properties that don't depend on the size of the volume or the pressure, right? These are properties that don't depend on pressure. Okay? All right, so we have, with that constant defined, we can now write our chemical potential like this. kBT ln P over P naught. I guess I've been, just to be consistent, I'm just going to write this as the naught on the bottom. Okay, so kBT ln of P over P naught plus our mu naught. And I'll put that this is a function of T here. All right? And so this expression we have is essentially the chemical potential of an ideal gas. All right? Okay, so once again, just combining quantum mechanics and thermodynamics, we were able to develop an expression that describes the chemical potential of a system just based on measurable properties. The last thing I want to cover is, we focus on internal energy and entropy, But we could also combine quantum mechanics and thermodynamics in order to calculate additional thermodynamic potentials. So can also derive additional thermodynamic potentials, and we would do that, as we saw before, using the method of Legendre transforms. Okay? Alright, so just to give you one example, for the Helmholtz energy, which is a function of temperature, volume, and the number of molecules in the system, by definition, using the Legendre transform, that's just equal to the internal energy minus Ts. Using our Sackur tetrode equation, we have formulas for both U and S. So we just plug them in. And so based on the Sackur tetrode equation, we could describe the Helmholtz energy like this. Natural log 2 pi m kBt divided by Planck's constant squared to the 3 halves. Then we have our exponential of 5 halves divided by n times v. Right? So this is how we could calculate the Helmholtz energy. Or we could use the alternative form of the Helmholtz energy that had the internal energy baked in. So 3 halves n kBt, n kBt, ln of u divided by n to 3 halves v over n plus 3 halves, there's a 5/3 here, plus ln 4 pi m over 3 Planck's constant squared 2, 3. Okay? Alright, so this is a alternative but equivalent form for describing the Helmholtz energy.